Okay, so I wanted to show you how to use EDA Playground as a way of getting to learn about Verilog without having to go through the pain of making Vivado projects, because Vivado, you've seen it, it takes a while for everything to run and get set up. And so I found this website where you can play around with Verilog code to a significant degree and work through some of the examples that we'll be doing in class and use that actually to help develop your lab work as well. So it's called EDA Playground, and I've already set up an account on there. It was very easy because I have a Gmail account that I use for things that I'm worried about getting spammed on. So I just used that Gmail account and logged in with that. I haven't seen a lot of spam coming from EDA Playground, but you might want to be cautious and set up a Gmail account if you don't have one, or there's other ways you can authenticate into this website. But when you go there, you get a couple of windows. One is called Design. If you zoom in on that, you can see it says Design. The other side is testbench. Okay, so the basic idea here is you have designs that you're trying to work through, get the logic right, get it to where it's doing what you want it to do. And then you have some code that helps you run a test bench to see if everything is working right. Okay, so every time you do an example, you can set up something that this website calls a playground. And I have a couple that I've set up, so look at your playgrounds. I'm going to click on number representations because this is the first one that I want to show you. Okay, so normally this side of the screen you would have a design, but we're not instantiating a design. We'll talk about that more in a second, but we're just making an example of a module that you can use for a test bench. Okay, so typical of a test bench, it's still a module, so notice I have module defined here, in module defined down here. All right, so that's giving me the scope of the module. All right, then I've defined some registers, and I used different sizes of registers, and in one case I have a signed register, and the other case I just leave it unsigned, and I wanted to just show you that you can play around with different types of literal assignments. Okay, so remember in documentation they call literals the constants that you assign things to. That's a little different than the book where we were talking about literals with K-maps. So sometimes we use the same word for different things, and you have to keep it straight from the context. All right, so the next thing I want to point out is that there's a block that's set up that's called an initial block. All right, so Verilog is going to run this initially. That's why it's called an initial block. There's another type of block that we'll use later called an always block, and we'll get to that when the time comes. All right, so if you have more than one line of code that shows up in a given initial statement, you need to frame that with a begin and an end. All right, so there's the markers of that. So you need to pay attention to the syntax so you won't get super frustrated in the lab. All right, so we have initial, I could cut that away. You'd start with this, begin and then end, and then you'd enter your text in to do what you want with the test bench. Okay, so a couple of new things I want to talk about. First of all, I've defined a register, so I'm going to store data in a register. You've read about this, hopefully in the little document that I put up on Canvas, but I'm going to put this binary pattern into the register A, and then I have next system tasks that I can run within Verilog that aren't actually part of the synthesis kind of steps that you would use in Verilog. It's just talking about your development system, and it's given a way of displaying outputs, for example. All right, so this first one that we're going to use is called $display. There's some others that we're going to use, $monitor. They're slightly different, but let's just use display. Display will take what happens at a given time instant and display what the value of the register would be. All right, so I'm gonna define A to be a certain binary pattern, and then I'm going to display that in different formats. All right, so I think you're taking C and or will take C or have taken C, and this should look a little bit familiar too because some of the codes that you use for displaying formats are similar, where we use the %B for binary, %H for hex, %D for decimal, and we can make this show up in different formats. So what I'm going to do next is, well, I'm going to talk about a few other things before I run this code. The next thing you need to know about is the pound sign. So remember from the documentation, normally all these assignments would happen at the same time, but within a test bench, you can use a delay parameter. And so this is saying delay this by 5 time ticks, okay, depending on how you set up time ticks. We'll talk about that when we get to it in a later section. So initially, A is this, and then we're going to wait 5 time ticks, and we're going to make A be a different definition. Then we're going to wait another 5 time ticks and let A be a different pattern. And I'm assigning the different registers at different times, all 5 time ticks apart. There's nothing magical about 5. Some people would use 1. Some people use 10. I think there are certain cases you could have logic that takes a while to propagate, and sometimes, you know, pound 1 might not be enough. But the simple stuff we're doing, it's not that big of a deal. Okay, so the next thing I wanted to show you is what happens if I assign this to be a negative number. All right, so I have A is equal to minus, and then the first thing here is the number of bits. Okay. I don't know if I intentionally used 6, but let's make it 5 since A is a 5-bit register. All right. And then I have this displayed in both decimal and hex. All right. And I do the same thing with, no, I don't do that. Well, let's just run this and see what happens. Okay, so I hit run, and what happens is, let me bring this up. I get displayed values from this display system command. Okay, so the very first one, 10110 is what we'd expect, 16 in hex, and we can convert that to decimal, and it will give us the decimal value. All right, so let's go down to the -5. All right. -5 D4. Okay, so D4 is hex 1C. Okay, so if you take 1 times 16, that's 16 plus 12, that would be 28. Okay, but this was -5 D4. Okay, so why would it be 28? Well, if it's a negative number, that would be represented in 2's complement. 5 bits, remember what 2's complement is. You take 2 to the 32 minus the number, the magnitude of the negative number. So 2 to the 32 minus 4 is 28. And so that's what we would expect here, because it's taking the unsigned representation of the -4. If I change this to signed, and reran it, so say rerun, okay, with the signed representation, these numbers turned out differently. Like the 16 became -10. Why? Because this is a 5-bit number. There's a 1 in the most significant bit position. All right. -4 turned out to be -4 because we're representing that in binary. Okay, so I have a few of these worked out. I wanted to show you this particular test bench. The cool thing is, I think you'll just be able to link to this, and it should work. And when you set up your own account, you can take a linked playground, play around with it yourself, and you don't have to worry about it messing up in my playground. Okay, so I want you to try that. I'll send you the link and you can play around with number representations in Verilog.